Namaste everyone. So in the last class we have discussed about the magnetic field and the magnetic force. What are the properties of magnetic field and what is the source of the magnetic field, how this magnetic field is created. And also we have seen that the magnetic force, when a charge moves in the presence of magnetic field, a force acts on the charge, right, and that force is called as magnetic force. So the expression for magnetic force acting on the charge in the presence of magnetic field, F is equal to, in case of single charge, F is equal to Q into V cross B. So this is the expression for magnetic force acting on a single charge which is moving with the velocity V. So velocity is a vector quantity, B is also a vector quantity, force F is also a vector quantity. In order to denote the direction of velocity, magnetic field and force, we have one rule, that is nothing but Fleming's left hand rule. Using this Fleming's left hand rule, we can give the direction of magnetic force acting on the charge. So first of all, you have to stretch the first three fingers of your left hand. The forefinger gives the direction of magnetic field, middle finger gives the direction of motion or it gives the direction of velocity, and the thumb gives the direction of force. So F is equal to Q into V cross B. If, or what is the expression for magnitude of magnetic force? The magnitude of magnetic force, F is equal to Q V B sin theta. If theta is equal to 0, what is theta? Theta is the angle between velocity and the magnetic field. If this represents velocity and this gives magnetic field, then angle between these two is nothing but theta. If theta is equal to 0, that means if velocity and magnetic field, they are parallel to each other, if B and V are parallel to each other, if this is the direction of magnetic field and the particle is also moving in the same direction, then we say that B and V are parallel to each other. In that case, theta is equal to 0. When they move parallel to each other, F is equal to 0. That means no force acts on the particle. No force is acting on the particle means the particle will not change its direction, it will move in straight line. If theta is equal to 90 degree, that means the angle between velocity and the magnetic field, angle between these two is 90 degree. If they are perpendicular to each other, if this is the direction of magnetic field and this is the direction of velocity, if they are perpendicular to each other, if the particle is moving like this and the magnetic field is like this, then we say that V and B are perpendicular to each other. In that case, maximum force acts on the charge. So how much force acts on the charge? F is equal to B Q V. So this force changes the direction of motion. That means if V and B are perpendicular to each other, then the charge or the particle will follow circular path. It will follow circular path only when V and B are perpendicular to each other. If they are parallel to each other, then no force acts on the particle and it will move in straight line, right. So this much we have seen in the last class. Now today let us see what is the expression for force, what is the expression for magnetic force acting on a current carrying conductor which is placed in the external magnetic field. So, let us derive an expression for magnetic force acting on current carrying conductor. Which is placed in the uniform magnetic field B. So, let us see what is the expression for magnetic force acting on a current carrying conductor which is placed in the external magnetic field. For that, let us consider uniform magnetic field. So, this is how we represent uniform magnetic field. So, the field is uniform, and one more thing, when we use cross mark, if the field or if the magnetic field is going into the plane of the paper, then we represent that using a cross mark. Here we are using cross mark, that means the magnetic field is going into the plane of the paper. If the magnetic field is coming out of the plane of the paper, then it is represented using a dot. So, here we are using cross mark. So, we can say that the magnetic field is going into the plane of the paper and the magnetic field is uniform. So, here we are placing one current carrying conductor. So, let us consider one current carrying conductor, and this current carrying conductor is placed in this uniform magnetic field. Let L be the length of the conductor. L is the total length of the conductor and A is the area of cross section. Let A be the area of cross section and L is the length of the conductor and I be the current flowing through the conductor. In case of conductor, we have large number of free electrons, right? So, charge carriers are nothing but the free electrons. So, due to the motion of charge carriers, we have current or we have electric current. When we get electric current, when charges move from one place to another place, we have electric current. So, let I be the current through the conductor. Current through the conductor. L be the length of the conductor. L be the length of the conductor. I be the current through the conductor and A is the area of cross section. Let A be the area of cross section. So, this is area of cross section, this is total length of the conductor and I is the current flowing through this conductor. So, what is the total volume of the conductor then? Total volume of the conductor V is equal to, if this is the area of cross section and this is the length of the conductor, then A into L is nothing but the total volume of the conductor. So, V is equal to A into L, area meter square, L is in meters. So, meter square into meter is nothing but meter cube. So, which is nothing but the volume. So, V is equal to A into L. Now, you just imagine that the charge carriers are moving in this direction. All the charge carriers are moving in this direction. That means this is the direction of velocity. Direction of velocity is upwards. Let us divide this total volume into number of unit volumes. So, this conductor or total volume of the conductor is divided into large number of unit volumes. In one unit volume, there are n number of electrons. Let small letter n be the number of electrons or the number of charge carriers present in unit volume. So, n is the number of charge carriers present in unit volume. So, let n be the number of charge carriers present in unit volume V or in unit volume. In one unit volume there are n number of electrons. Then how many charge carriers are there in total volume V? So, the total charge carriers, in volume V is equal to, how many charge carriers are there in the total volume V? N into V. So, N into V. We know that V is nothing but A into L. So, this is the number of charge carriers or the total charge carriers present in this volume. Charge on single particle is represented by Q. Then what is the charge on NaL charge carriers? NaL into Q. And also the magnetic force acting on a single charge is the magnetic force acting on a single charge is F is equal to Q into V cross B. Here the charge carriers are moving from one end to another end, or in other words we can say that the charge carriers are drifted from here to here. Charge carriers are drifted. So, here we have drift velocity. So, in the place of V, we have Vd. So, F is equal to Q into Vd cross B. This is, in case of single charge, the magnetic force acting F is equal to Q into V cross B. But we know that there are NaL charge carriers in this conductor. So, the total force acting on NaL charge carrier is, so the total magnetic force acting is F is equal to NaL into Q. For a single particle, charge is Q. For single particle, charge of the particle is represented by Q. But here we have NaL number of charge carriers. Then what is the total charge? NaL into Q. So, NaL into Q into Vd cross B. Vd is nothing but the drift velocity with which all the charge carriers are moving from one end to other end. So, F is equal to We know that I is equal to N E A into V D. In current electricity you have studied this equation, right. So, I is equal to N E A V D. E is nothing but the charge. Here instead of E we have Q. So, I is nothing but N Q A into V D. V D is the drift velocity, A is the area of cross section, N is the number of charge carriers per unit volume and Q is the charge. So, N A Q V D is nothing but I. So, I into, here we have L cross B. Here we are taking L as vector quantity. Here L is, length is nothing but the vector quantity. L vector, magnitude of L vector is L and its direction is same as that of current I. So, L is taken as a vector quantity here and its direction is same as that of current I. So, F is equal to I into L cross B. In terms of magnitude, F is equal to B I into L sin theta. Here we have cross product L cross B. So, A cross B is nothing but AB sin theta. So, here we have L and B. So, L cross B is nothing but LB sin theta. So, this is the expression for magnitude of magnetic force acting on this conductor. So, this is the magnitude of force acting on the conductor. Now, let us see what is the direction of force acting on this conductor. For that, you have to use Fleming's left hand rule. So, using Fleming's left hand rule, we can give the direction of magnetic force acting on this conductor. So, if this is the direction of motion or if this is the direction of velocity of the particle, then we know that always middle finger gives the direction of velocity. So, velocity is upwards. So, this is upwards and also magnetic field is into the plane of the paper. So, B, magnetic field is into the plane of the paper, this should be like this and velocity is upwards. So, this is it. So, B gives the direction of magnetic field and V gives the direction of velocity. Velocity is in upward direction, magnetic field is going into the plane of the paper. Then what is the direction of force? Thumb gives the direction of force. So, the force acting on the conductor will be in this direction. So, this is the direction of force. If velocity of the charge carriers is in the downward direction, that means if V is in the downward direction, if this is the case, magnetic field is same, it is going into the plane of the paper, velocity, direction of velocity is downwards. So, in that case, magnetic force acting on the conductor is like this. So, using Fleming's left hand rule, we can give the direction of magnetic force acting on this conductor. Here we are assuming that the velocity is in upward direction. So, this is the direction of magnetic field. So, this is the direction of velocity. So, this is the direction of force. If this is the direction of velocity or if the charge carriers are moving in downward direction, in that case the force acts in this direction. So, this is about the magnetic force acting on a current carrying conductor which is placed in the external magnetic field B, and the expression for force is F is equal to BIL sin theta. In case of single charge, the magnetic force acting on the single charge is F is equal to BQV sin theta. In case of current carrying conductor, the magnetic force acting on it is F is equal to BIL sin theta. Here theta, what is theta? Theta is the angle between I and B. I and B. So this is about the magnetic force on current carrying conductor. Take down. So when a charge moves in the magnetic field, the force or the magnetic force acting on the particle F is equal to BQE sin theta, and I hope that you all know about this magnetic force. So F is equal to BQE into sin theta. In order to represent force, or if you want to find out the direction of force, because force is a vector quantity, you have to use Fleming's left hand rule. If theta is equal to 0, we know that theta is angle between velocity and the magnetic field. Always remember, magnetic field is represented by forefinger, velocity is represented by middle finger, and the force is represented by thumb. So if theta is equal to 0, what is theta? Theta is the angle between velocity and the magnetic field. If angle between these two, theta, is equal to 0, that means there is no angle between magnetic field and velocity, or we can also say that the direction of magnetic field and the velocity are same. If the magnetic field is inverse, particle is also moving in the same direction, then angle between them is 0. In that case, the particle moves in straight line, because no force acts on the particle, there is no change in direction, so it moves in straight line. If theta is equal to 90 degree, that means angle between B and V is 90 degree. If they are perpendicular to each other, then theta 90, sin 90 is 1, F is equal to BQ into V. So the maximum force acts on the charge. In that case, force acting on the charge F is equal to BQ into V, because theta is 90, sin 90 is 1, no need to write 1. So F is equal to BQV. So this is the maximum force acting on the charge when it is in, or when it is moving in magnetic field. So in that case, the particle moves in circular path. When theta is equal to 90 degree, the particle follows a circular path. When theta is equal to 0, it moves in straight line. If theta is not equal to 0 and theta is not equal to 90 degree, if this is the case, then the particle will follow which path? Whether it follows a circular path or it follows straight line. That we have to find out. So here theta is not equal to 0, theta is not equal to 90 degree. You just imagine that this is the direction of magnetic field. So the magnetic field is in this direction. It is a vector quantity, so it is directed along x-axis. Magnetic field. If magnetic field is like this, if velocity, direction of velocity is like this, then we can say that B and V are perpendicular to each other, theta is equal to 90 degree. Or if velocity and magnetic field, they are in the same direction. If this is the direction of velocity and this is the direction of magnetic field, then there is no angle between B and V, theta is equal to 0, so the particle moves in straight line. If the direction of velocity is like this, 0, theta is not equal to 90 degree, theta or velocity vector is making some angle with the magnetic field, and that angle is not equal to 0, not equal to 90 degree. In that case, so this is theta. So I will draw here. So this is the magnetic field, this is x-axis, and this is y-axis, and this is z-axis. So magnetic field is along x-axis. So this is y-axis. So the direction of velocity is like this. If this vector v and b, if theta is equal to 0, then the vector will be like this. Theta is equal to 0. If theta is equal to 90 degree, then it is like this. Here theta is not equal to 0, not equal to 90 degree. Therefore, so this is the direction of velocity. So this is theta. What we have to do now? This vector is having two components. If a vector is lying in x-axis, then we can say that it is having only x component and its y component is 0. Similarly, if a vector is lying in y-axis, then or if it is parallel to y-axis, then we can say that it is having only y component and its x component is 0. But here, the vector is in a plane, right? That is, this vector is having two components. One is x component along x-axis, another one is y component which is along y-axis, or one is parallel component, another one is perpendicular component. We know that here we are resolving v into its components. Velocity vector is resolved into its components. One is x component. So x component is here, right? Vx. X component of v is represented as vx and y component of v is represented as vy. So vx is equal to, we know that x component of v is v cos theta. Similarly, y component of v is v sin theta. Or this is the parallel component, v parallel, because this component is parallel to x-axis or it is parallel to magnetic field. It is along the direction of magnetic field. So this is the parallel component. V parallel is equal to v cos theta, and this is perpendicular to magnetic field B. So it is the perpendicular component. So it is represented by v perpendicular. So v perpendicular is equal to v sin theta, v parallel is equal to v, parallel component of v is v cos theta. Now, due to this component, so due to v perpendicular or due to the perpendicular component of velocity, perpendicular. Now we just consider only this component, that is v sin theta, right? For this component, theta is equal to 90 degree. Theta 90 means F is equal to BQV. Maximum force acts on the particle, right? Force acts when theta is equal to 90 degree, right? When theta is equal to 90 degree, the particle follows circular path. So due to this component, the particle will follow circular path. It will follow the circular path due to this perpendicular component, right? Because along y-axis, theta is equal to 90 degree for this component. We are resolving v vector into its component. One component is along x-axis, that is v cos theta. Another component is along y-axis, that is v sin theta. So due to this perpendicular component, theta is equal to 90 degree, so F is equal to BQV. There is force acting on the particle. Due to that force, it follows circular path. due to this parallel component. So due to this parallel component, we know that when velocity is parallel to magnetic field B, it will not change its direction. It will follow a straight line. Right? The particle will move in straight line. So due to this parallel component, the particle moves in x-axis, or the particle will move along the direction of magnetic field due to the parallel component. The particle will follow circular path perpendicular to magnetic field due to this perpendicular component. Right? Due to the superposition of parallel and the perpendicular components, the particle will have both circular motion, this is nothing but circular motion and linear motion. Circular motion and linear motion. So this is the path followed by the particle when theta is not equal to 0 and when theta is not equal to 90 degree. So I will write here, due to perpendicular component, the charge will experience magnetic force, that is F is equal to BQV, and it moves in circular path. So this is the first point. So the second point is, due to V parallel, due to this parallel component V cos theta, the charge will move in straight line. Here we are having both the components. So due to the superposition of circular motion and linear motion, third point is the superposition. Due to the superposition of circular motion and linear motion. Linear motion is along x-axis and circular is along this direction. So circular motion and linear motion, the path will be helix, or the particle will follow helical path. Right? So due to this component, it is having circular path. Due to this parallel component, it will have linear motion. After that, again it will have circular motion and linear motion. Circular motion and linear motion. So this is nothing but the helix. So the particle will follow helical path when angle between velocity and the magnetic field is not equal to 0, not equal to 90, not equal to 180 degree. Right? So the distance moved by the charged particle during one rotation. So the particle is here, so it will move like this: circular motion and linear motion, circular motion and linear motion. So the distance moved by the charged particle during one rotation. So this distance is nothing but pitch. So the distance moved by the charged particle during one rotation by the charged particle during one rotation. So during one rotation, it is the distance moved parallel to the magnetic field B along the magnetic field B, parallel to magnetic field B. So this is the distance. So we know that speed is equal to distance by time, right? This is the expression for speed. Speed is equal to distance by time. Distance is equal to speed into time. Distance is equal to speed into time. So distance moved by the charged particle parallel to the magnetic field is nothing but pitch, and it is denoted by P. Speed or the velocity. So along the direction of magnetic field, so which component you have to consider? Along the magnetic field we are having the parallel component, that is nothing but Vx. So velocity is nothing but Vx into time. Here we are considering one complete rotation. So the time for one rotation is nothing but the time period, right? Time for one rotation is called as time period. So time period is represented by T. So P is equal to, pitch P is equal to, Vx is nothing but V cos theta into time period T. So this is the expression for pitch. Okay. So when theta is equal to 0, particle will move in straight line. When theta is equal to 90 degree, it will follow a circular path. When theta is not equal to 0, not equal to 90, not equal to 180 degree, it will follow helical path or helix. Take down.